This is it. This is Wednesday night. So where some great and glorious homework writing is going to go down for your next dozen Wednesdays. But not tonight. Tonight I'll just tell you some stuff about proofs. Okay, so as mentioned, this is kind of like an optional lecture in the sense that the material I will talk about today will not be on the test, although I will be talking about how to write proofs to some extent and tips for how to do that. So that will be a key component of the course. Okay, so speaking of proofs, let me show you what we're going to talk about tonight. 3 parts, all about proofs. Number 1, what is a proof? Number 2, how do I find a proof? And how do I write a proof? Okay, so let's start with number 1. What is a proof? Well, let me show you, let's start with some examples. We'll see what you think. So here's a proposition. Let's let n be any positive integer and then do the following algorithm. If n is even, divide it by 2. If n is odd, then triple it and add 1. The proposition says that you'll eventually hit 4, 2, 1, then it goes back up to 4, 2, 1, and it'll repeat like that forever. So for example, if n is 10, it's even, so you go to 5. That's odd, so you go to 16. It's even to 8, 4, 2, 1, and then it repeats. Okay, so it worked for 10. You could try 11 in your head. Okay, so here's a proof. Many people have tested this, including for all numbers less than 1 quintillion. And no counterexample has been found. So is this a proof? No, you tittered, so I guess not. Yeah, in mathematics, this is not an acceptable proof. If it says for all n, you have to give a proof for all n. You cannot just test a bunch of cases. I put this up here, though, to contrast it with, let's say, other parts of science. Like in physics, this kind of thing is a proof, right? That's how you test things in physics. You just try many examples, and if you don't find a counterexample, then that's the law of nature. But that's not how we do it in mathematics. Okay. This is actually a conjecture. It's called the Collatz conjecture. Actually, it's kind of related to some of the topics we'll be talking about in computer science about computability over the next couple of weeks. This has a scary-looking integral in it. This is a proposition. For any odd positive integer n, this integral equals that. Okay, you don't have to know calculus really to do this course. So I've put this up only as an example. But it says that the integral of this thing is pi over 2. This thing times this thing, you also get pi over 2, etc. So you could go back and remember how calculus works and try to check this for n equals 1, n equals 3, n equals 5. I kind of myself forget how to integrate. So whenever I need to integrate something, I use a computer. Let me show you that. I'm a Canadian, I guess, so I like this Maple, but it's similar to Mathematica or whatever. So let's just try it. This is supposed to be pi over 2, so it worked. Yeah. And then this is supposed to be pi over 2. Oops, I skipped one. This one's pi over 2. Yeah, pi over 2, pi over 2, pi over 2, pi over 2, pi over 2. Okay, so we're good, right? So we checked it for 1, 3, 5, 7, 9, 11, 13. So basically, by induction, it should be true, right? You would be forgiven for conjecturing it. There was one line there still, though, that I didn't execute. Because if you execute this, has to think about it. Actually, that's the answer. It's not pi over 2. It's kind of amazing. Actually, people discovered this when they were testing programs like Mathematica, and they were like, well, we got a bug. But actually, it's true. That calculation is correct. So this is not a good proof either. Just again goes to show you that even when something really seems like it must be true based on the cases you test, might not be true. Okay, let me show you another one, though. Here's a proposition. Let's say you're given a solid ball, like good old-fashioned ball in 3-dimensional space. The proposition is that there's no way to break it into finitely many pieces and then reassemble those pieces and get 2 balls of the same size as the original one. Okay, so the proof for this one, it says, this picture is impossible. The proof for this one is, this is obvious, right? Come on. Well, actually, that's not true. Not only is it not obvious, it's not even true. It's actually, there is a way to do it. It might sound crazy. It's kind of a crazy math thing. But this is a theorem that you can do it, called the Banach-Tarski Theorem. Okay? Again, you do not need to know this for 251, but this is for your own culture's sake. So yeah, it does not seem possible or obvious, right? The proof is a bit crazy. You use something called group theory, which actually we are going to talk about in 251. And you might say to yourself, how is this possible, right? These have volume 2, which is correct, or they have twice the volume of this ball, so how can that be possible? Well, it uses a crazy notion, like a weird mathematician's notion of pieces, and they're like these weird scatterings of points for which you cannot meaningfully define volume. So yeah, in math, some things can be tricky, is what I want to say. OK, how about this one? 1 plus 1 equals 2. Now, having seen the previous slide, you might be like, well, now I don't know anymore. Like, this is obvious. Okay. This is obvious, OK? It's OK. This is obvious. 1 plus 1 equals 2, all right? You can write this in your homework. It's fine. Yeah. Yeah, well, we'll see. But yeah. OK, so maybe this actually isn't obvious if you're 3 years old, and maybe it requires a proof to a 3-year-old. But at this stage of the game in our lives, this is fine. OK? But it raises the question of what is a proof? Why is it OK to say this is obvious in one case and not in another case? And why is it not sufficient to just check a lot of cases and say that it seems to be true? Well, on one hand, in math, there are agreed upon rigorous rules of deduction, and proofs are either right or wrong. But at the same time, as I'll try to kind of explain a little bit in this lecture, what constitutes an acceptable proof is kind of a social construct. Like it's OK to say 1 plus 1 equals 2 is obvious, if you're an undergraduate at Carnegie Mellon. Maybe not if you're a 3-year-old. You have to think about it a little bit. So we'll talk about this, because it comes up when you're trying to write a proof, for example, on your homework that convinces the TAs. In fact, computer science can kind of help with some of these issues, alleviating and understand these issues, and I'll talk about that also in this lecture. OK, so let me tell you some stories about proofs throughout the history of mathematics. So I guess the story supposedly starts back with this guy, Euclid, who wrote a famous geometry book in Elements, called The Elements, 2,300 years ago, where he was the first person, I guess, to kind of say that, for mathematical facts, we should actually try to deduce them from a set of axioms in a logical and rigorous way. Okay, and he did his best to do that. He wasn't perfect at it, but, he got off to a good start. So he was kind of the first person to, look at proving mathematical facts in a rigorous way. It was imperfect, as I said, and, true rigor sort of only started to happen in the 19th century. And people thought about, transitioning into fully rigorous proofs then, and they kind of eventually came to understand that you could completely rigorously formalize proofs using logic, first-order logic. So then they got kind of excited about it, and this was also at the same time, from yesterday's lecture when, Hilbert was talking about finding an algorithm to solve problems in mathematics or decide statements in first-order logic. So this is part of that general mathematical excitement of the time. These two people, Russell and Whitehead, decided they're going to try it, to try and just prove everything in math in a completely rigorous way, starting from super basic axioms. So they started a book project to do this called Principia Mathematica, and they worked on it for 10 years or 20 years, I can't remember, a long time. So they started with some basic axioms, and they developed number theory and some arithmetic, real analysis, using purely formal logic. I'll give you a taste of what it looks like. This is page 379 of their work. And you can just see it's super painful. I mean, it really looks like programming machine code. Actually, there's kind of a nice analogy between coding and writing proofs. In fact, on this page, yeah, what were they proving? They were proving 1 plus 1 equals 2 on this page, 379. So it took a lot of work to build up this entire machinery of doing proofs in a completely 100% rigorous way, just pure axiomatic deduction. I also like how they're this proposition is occasionally useful. And actually, to be fair to them, they probably could have got to 1 plus 1 equals 2 on page 30, but they were setting up all these other parts of their logical system, so that's why it took so long. Okay, so after this, they kind of just ran out of gas. They were like, this is too exhausting, never mind. And it kind of, but largely based on this, it became agreed upon by mathematicians that, okay, if we really wanted to, we could take all the proofs that we write down in our mathematics journals and try to rigorously, make them 100% pure logic deductions from the axioms. But it was too exhausting. Nobody wanted to do that. And so they were like, okay, let's switch back to the way we normally do it, which is to just write stuff in English or other natural languages. But of course, that raises the question of whether, English language proofs are really sufficient, whether they can really be rigorous enough to give us mathematical certainty about the things that we're trying to prove. So let me try to tell you some anecdotes on this topic. Maybe one of the more famous anecdotes concerns this fact, the four-color theorem. This is a famous problem in mathematics. It was posed by somebody in 1852, and they conjectured that whenever you have like a two-dimensional map of regions, it can be any like map that divides a piece of paper into regions, there's always a way you can color the regions with at most four colors such that the adjacent regions never get the same color. So here's like a picture of the 48 continental United States. And it's colored with four colors, pink, purple, green, and yellow, in such a way that, indeed, no two states that border each other have the same color. Okay, so this person conjectured that it was always possible to do this, no matter what the map was. And it became a pretty popular problem, and for a long time, nobody can solve it. Until like 40 years later, when a pretty well-known mathematician, Kempe, proved it in the American Journal of Mathematics. And people were very happy about that. And actually, then 1 year later, another mathematical physicist, Tate, gave a different proof, like an alternative proof, in a Scottish journal. So that was cool. It took a long time. But actually, 10 years after that, another mathematician, Heawood, found a bug in Kempe's proof. So he was wrong. And the mathematicians were like, well, thank goodness we have Tate's proof still. And then 1 year later, Peterson found a bug in Tate's proof. Okay, and so then it went back to not being a theorem anymore because nobody knew how to actually correctly prove it. It shows you some of the, risks that are involved in having, a very long, complicated proof that's written just, in English. And, these guys were not jokers. I mean, Kempe was a pretty famous mathematician, and people had studied his proof a fair bit. So that was 1890, and nobody really made any progress for another 70 years. Something like that, 80 years, until a mathematician called Heesch, he developed, he worked on the problem, proved some more lemmas, proved some more things about it. He didn't fully solve it. But one thing he did show was that he got it down to a situation where he's like, okay, we could complete the proof of this theorem if we could just check a certain finite number of cases, like some enormous number of cases. You have to actually prove the theorem for all maps, but he figured out a mathematical way to reduce it to checking a finite number of cases. So that was interesting. Okay, and then 7 years later, they started to build computers, and Apple and Hawken, two computer scientists, were like, well, now we have computers. Maybe we can actually just check all these cases. So they actually also did some mathematics to organize the whole process and understand the cases and further the theory. But they also wrote like a massive amount of computer code that first computed all the cases, like enumerated them, of which there are like 2,000, and then also checked them. Okay, and that took 1,200 hours of computer time. And they hit enter or whatever the keyboard said back then, and it ran for 1,200 hours, and it checked out, and it was like done. And they were like, okay, done. We proved the theorem. So they claim that that was a proof of the four-color theorem. So actually, now we're going to try a poll. This will be our first practice poll. Yes, get out your phone. I've never done this before, so I hope it works smoothly. Let's try this. So now I go to Piazza. I publish the poll. Okay, well, let's see if that works. So can you see this poll? Let's have a TA. Are you guys enrolled in the, yeah? You can see it? Okay, you should vote. Okay, let's all vote. Oh, I got to figure out what the results are, too. Okay, so the poll question is, what do you think? Is this a proof? All right, we're getting some results. Oh, pretty good. We got 43 votes. All right. How many are you, like 100? Yeah, pretty cool. All right. All right, pretty cool. 100. All right. All right, well, you can keep voting, I guess, but let's see. So it's a pretty good spread. 60% say yes, and 40% say either no or I don't know. Actually, I don't know is pretty reasonable because, I don't know, you didn't know a lot of things about the situation. But it's a very good question, I think. I think it's reasonable to answer it either way. So in fact, it was very controversial when it happened in 1969. I mean, people also in the math community were kind of split about whether, like, they really proved it. So actually, let me ask you, like, what are some reasons you might say no? Okay, if you say yes, maybe you think it's yes. But what are some reasons you might have for not considering this to be a proof? Yeah? Yeah, that's a very good point. The computer may have a bug. Actually, in fact, that could be divided into at least two possibilities. Yeah? Yeah, even more. So the possibilities were like there's like kind of an underlying theoretical bug about the code that you didn't consider. Maybe you implemented it wrong. Maybe the compiler had a bug. Maybe the machine code has a bug in it. Yeah? Yeah, I mean, it does take it into the physical world. So, for example, I mean, I don't know much about physics, but like maybe like a neutrino like hit the circuit at the wrong time, and yeah, caused like a bit to be flipped and made the answer yes instead of no. Other possibilities? Yeah. That's true. The same thing could happen with the human brain. That's right. So maybe everybody who reads the proof simultaneously gets the neutrino in the brain that. No, but that's a valid point, right? Yeah. I mean, these are probably unlikely events, but other comments? Yeah, I mean, that's true. That's something I said at the beginning. Like, yeah, what I said at the beginning is it's true that in some extent, you know, what counts as proved is a little bit like what mathematicians agree has been proved. And so if the mathematicians don't all agree, then maybe it doesn't count. I mean, yeah. Any other ideas or reasons why you might not consider it a proof? Yeah? The comment was maybe you didn't enumerate all possible cases. That kind of gets at the math portion of the proof. So there is like a math portion that he did, this other person, that said, if you could check all of these cases, then by some other mathematical deductions, it would follow that it holds for all planar maps. Now that also could be wrong, although that part is more like a traditional proof in the sense that, you know, it's written in English in a math journal or something. But, you know, this could also be faulty. Other comments? I had some other things. We kind of said some of these. You know, you could say no human could ever hand check two cases. Actually, this one is kind of interesting in the sense that, you know, why do you want to prove things? I mean, one of the main reasons we want to prove things in mathematics is we want to know why something is true. And we didn't really get this from this proof, right? You like ran the computer for 1,200 hours, and it's like, hey, I checked all the cases. You still don't really know the reason why every map can be colored with 4 colors in this way. So yeah, let's see what the final total was. Yeah, 60-40. All right, so now I have to close this somehow. All right, well, let's assume that works. Cool, yeah. Well, I'll tell you, not the end of the story, but I think by now most people are pretty satisfied that they proved it. I mean, some people are still uneasy with calling it a proof, but at least people say they give credit to Apple and Hawken, and most people accept that it's a true theorem. Actually, there's a few more anecdotes on this story. So Apple and Hawken actually, after they published their first result, they went back and they found some mistakes in their work, thinking how they organized the cases. And they called them either type 1, type 2, or type 3 mistakes. I don't know where type 2 went, but they found empirically that whenever they found a type 1 error, whatever that was, they could fix it in a few minutes. Whenever they found a type 3 error, they would usually be able to fix it in a few days. And then this other mathematician, or well, he was a master's student actually, in 1980, he also went back and looked at their work and found 13 type 1 errors that they hadn't found and 1 type 3 error that they hadn't found. And he told them, and then they fixed them. And then they published a book in 1989 where they're like, okay, this time we fix it all. This time for sure it's done. So that's pretty satisfactory. And actually, I don't think anybody's found any errors in that. And also, one reason why people are sort of more happy with this particular theorem is in 1997, a simpler computer proof was found by these graph theorists that only involved checking 500 cases or something. So it still makes people somewhat uneasy, but I guess this had a somewhat satisfactory resolution. Actually, an even more satisfactory resolution happened in recent years. I'll tell you about that soon. Okay, that's one anecdote. This next anecdote is about an even mathier topic called the classification of finite simple groups. It's also related to group theory, a topic I mentioned in math. It's kind of like the theorem that tells you all the sort of prime numbers of the groups, whatever that means. It's not too important. But it's a theorem that it's pretty simple to state. It says every simple group, whatever that is, some mathematical object, is either in one of these 26 cases or one of these 7 families, something like that. Anyway, it's a fairly simple to state theorem. And people started working on it actually in the 19th century. And they've been working on it ever since. And hundreds of papers were written about it, trying to make progress towards proving this theorem. They were 10,000 pages long in total, or 20,000 pages long in total. And it went on and on and on, people contributing to this enormous proof. And then finally in 1983, this expert, Gorenstein, was like, okay, we did it. We proved it. That was the 20,000th page was the last one, done. And this was also a little bit suspicious, right? Because after time, only really super experts could figure out what was going on, and they basically had to take this guy's word for it, or him and the other people who are really into this theorem, because nobody had, except for a very small number of people, had read all these pages. And in fact, this guy did something a little bit naughty, which is that he said this when he actually knew the proof wasn't complete. But he really thought that people were getting so bored and they wouldn't be interested in this project at all anymore, that he kind of had to make an announcement to generate some excitement around it, which is pretty not nice. So the experts actually kept working on it because they knew they had to do this one more case of the quasi-thin groups or whatever that is. And then finally in 2004, these other two experts, Ashbacker and Smith, released another 1,200-page paper, and they were like, okay, this time it's really done. We got the last case. And it was somewhat of, again, a suspicious kind of circumstance, because you kind of had to take their word for it, unless you were one of these very few number of people that had read these thousands and thousands and thousands of pages. And so again, there's kind of some controversy as to whether or not the proof had been, that was a proof. Let's try another poll just for practice. Maybe I'll go on while you vote, but just in case. I'm actually curious to know what you think. So this is another poll saying, do you think it's really proven? So tell me what you think. I'm curious. Here's a genuine concern. People really talk about this, the possibility that everyone who really is in the know about this proof will die before they kind of really properly write down a proof that other people can understand. In fact, I spent a year in this tiny town surrounded by farms in New Jersey, and I met this person because her kid went to the same daycare as my kid. And then I later found out that she's widely considered to be the youngest person who kind of more or less knows the entire proof. So it's a serious situation. Now, they actually have, I mean, the experts on this have a plan. They're working on a 13-volume series of books that they expect to take about 5,000 pages that will actually contain like a more properly written version of the proof. I think they've completed like 6 of them so far. So hopefully we'll have like a semi-understandable version of the proof at some point. Although who's reading these 5,000 pages? I don't know. Let's see what you're thinking. Yeah. Fair enough. Let's keep our stats up here. All right. Resolved as funny. You might say, like, OK, what do these stories have to do? Isn't this a computer science class? Well, let me tell you something, actually. 1 month ago, a pretty well-known computer scientist, Latsi Babai, published a paper, not a crazy one. It's like 70 pages long. It's quite readable. Where he showed that this problem that we may talk about in this class, called the graph isomorphism problem, can be solved by a very efficient algorithm, almost a polynomial time algorithm. And actually, to me, in my personal opinion, this is like the greatest result in theoretical computer science in the last 10 years. It was like everybody was super in the know, was like super duper happy about this. Let me tell you a fact about the proof, though. The proof that it's correct relies on this, 10,000-page classification of finite simple groups theorem. Not in a super strong way, but if you want to be super convinced of this, you have to believe that other theorem. This also uses group theory in some way. So people in general, I think mathematicians generally kind of accept that the theorem is true, but they prefer not to, like, put their faith in it unless they really have to. Yeah. By the way, he's coming to talk about this amazing result here at Carnegie Mellon on January 22nd, if you want to see some group theory in action. OK. We've got time for a few more anecdotes. I cannot rob you of these anecdotes. Actually, the most famous theorem in mathematics that was proved, let's say, in our lifetimes, I think, well, my lifetime at least, was when Wiles proved Fermat's last theorem. But you might not remember that he proved it, and then 1 year later, well, actually fairly soon after, they found a bug. And they fixed it 1 year later, but it took like a 100-page paper. Here's another one. There's a pretty nice geometric problem called the Buseman-Petit conjecture. It's not important what it is. It's actually not so hard to understand. And it has different cases. And the last case that wasn't resolved was n equals 4. And this mathematician Zheng proved it in 1994. And this is like the most famous mathematics journal, Annals of Mathematics. As you might not be surprised to hear, given this lecture, it turned out that people found a mistake in his proof. And that naturally upset him. So he worked really hard to fix it. And he actually managed to prove the opposite, that it's false. And he wrote a paper in the same journal where he disproves the thing. Doesn't even refer to the earlier paper, actually. But it's pretty awesome that both, like, the statement X and the statement negation of X are like both proved in the same journal in a span of 5 years. That was pretty cool. OK, one more story along these lines. This is an ancient person whose name is this. That's true. I shouldn't make fun of a person's name, but it's kind of funny. Anyway, that was the patron of this more famous person, Kepler. And Kepler gave this Walkenfels a gift for New Year's, which was a paper, which had a conjecture in it. And its conjecture was about how, if you have like lots and lots of spheres, like oranges or cannonballs, what's the best way to pack them so you use up the most space in the most efficient way? And the logical idea is to stack them in this way you see oranges stacked at the grocery store, or the way they actually stack cannonballs. And it seems like the best way to fit spheres together that uses up the space in the most efficient way. And its conjecture was that this is the best way to do it. It's pretty hard to mathematically prove, though, that there isn't some crazier way to do it that will pack them even tighter. So that problem was pretty famous. That one was open for like 400 years until it was proved by this Pittsburgher. You can see him walking around Pittsburgh. Tom Hales, he's a cool guy, in a 120-page paper in the Annals of Mathematics. Well, I say it's 120 pages. It was 128 pages of normal math, plus it was like the four-color theorem, plus code to solve some 100,000 optimization problems that took 2,000 hours of computer time. So it's very much like the four-color theorem on steroids. And again, this is a famous problem. It's open for 400 years, so people took this very seriously. They're like, we got to really become satisfied that this is a proof. So this journal, Annals of Mathematics, they did a pretty cool thing. They're like, we're going to do it. Like normally when a paper got sent to a journal, like maybe 1 or 2 people will review it. They got a team of 20 people to review it. They worked on it for 4 years. Some quit, some retired, one of them died. They got to the end of the 4 years working on it, and they gave up. So at the end, they were like, we can't do it. We cannot, certify that this is a complete proof just because resolving this whole question of like, is the computer code correct and so forth and so on is too hard. But they were like, we're 99% sure it's true. And they published it. So that was cool. Tom Hales is a cool guy, though, and he was not satisfied with that. He's like a pure mathematician. He only works on like hardcore geometry. He's like, you know what? I'm going to get into this whole computer science thing. I'm going to code up a completely formal, 100% formal proof deduced straight from like pure axioms, just like Russell and Whitehead with their Principia Mathematica, and it'll do it in a computer-readable format so that it can be checked by a computer, just to like really prove that he proved it. And this was a big task. Now, there have been a lot of developments in this proof-checking area, so it wasn't as hard as it was for Russell and Whitehead. He made it an open source project he called it Project FlySpec, and it lasted for 10 years. And at the end, he did it. It's pretty awesome. So in 2015, he also hit enter. The computer did it, but in a better way, as you'll see. And he wrote a paper about this formal proof of the conjecture. So let me say a few words about computer-assisted proof, because it's an interesting topic, especially here at Carnegie Mellon. So this is actually an area of research in computer science that's quite hot right now. There's something called proof-assistant software with various implementations of it or people's research projects. And these proof assistants do 2 things. They first, if you give them a formally encoded proof of a mathematical theorem that like really does 100% of the steps in logic, it will just check that it's correct. And it also has some kind of like HCI aspect to it. It helps you find and code up these proofs, like translate English language proofs into like computer checkable, fully rigorous proofs. And as I said, it's making both these aspects better is a major area of research, especially at CMU. And I think it really helps for this issue of trusting computer-based proofs or trusting any proof. So Hall Light is the one that Hales used. And he ran it, and it verified his proof that he developed over 10 years. And it's pretty satisfactory, in my opinion, because even though his proof is 1 million lines long in computer code, you don't actually have to you don't have to trust that he coded it correctly, that those 1 million lines are correct, because Hall Light checks just that every line follows rigorously from the previous lines. And so you really only have to mostly trust that the Hall Light little text parser that checks that each line validly follows from previous lines is itself implemented correctly. And a lot of people have studied that. It's only 430 lines of code, so it seems pretty reasonable. Yeah? That's a very good point, too. And Hales takes all these issues seriously, and he encourages readers. He gives the statement of the theorem that he's checking, and he's like, it's on you, reader, to verify that you agree that this computer's statement of the theorem agrees with the meaning of the Kepler conjecture. And that was a pretty heroic effort. Now, it built upon, a lot of people had done this for other famous problems. So here are some famous theorems in math that have fully computer-checked rigorous proofs. Fundamental theorem of calculus, algebra, prime number theorem that was done at CMU, Gödel's incompleteness theorem, these other theorems. These are probably the 3 major ones. The 4-color theorem. So this is like the ultimate version of like the Apple and Hawken thing. So Gontier famously, working at Microsoft, gave a completely rigorous proof, computer-checked proof of the 4-color theorem. This is like the first 100 pages of the 20,000 pages of the classification of finite simple groups, this Fiat-Thompson theorem, and the Kepler conjecture. So it's a pretty cool area. I mean, kind of gone on a little diversion, but I like this topic a lot. So. And regarding your question, this is what the proof of the 4-color theorem looks like. Well, it's this plus 60,000 more lines. But this is basically the part where he states the theorem, and then, well, you have to read the rest of the code, but that's what it looks like. So it's actually kind of cool. It's like computer programming. OK. That is the end of all my anecdotes on what is a proof. And now I'll move on to the other two topics that are a little bit more germane to your work. Let me see how Piazza did there. Interesting. Did I close it? Let's close it. All right. Let's end with these two topics. How do I find a proof, and how do I write up a proof? OK, so this is more, OK, we're not going to be proving like the four-color theorem or whatever in this class. We'll be solving homework problems. But let's try to get in the mindset for how you can personally solve the homework problems. OK, so when I'm faced with a math problem, I have a personal philosophy. This is my own. When I do computer science research and math research on, they're hard problems to me, this is my personal philosophy. Make 1% progress per day for 100 days. And then hopefully you'll solve the problem. I mean, as we were talking about yesterday, math is pretty hard, and it takes a lot of effort, and you got to work at it. So this is what I tried to do. Now, you don't actually have 100 days for the homework, so your version is like make 15% progress a day for 7 days. But it's the same philosophy I think applies. It's also not just me that I think feels this way. So let me give you another quotation. This person is Terry Tao. He's probably regarded as like the most famous mathematician or the most powerful mathematician or a very famous mathematician who's alive today. He won like all the prizes, the Nobel Prize for Math, which is called Fields Medal. He won prizes that are worth money, which is very weird in mathematics. So he's won like $6 million worth of prizes. He's a very celebrated person. And like this is his story on how he solved problems. He said, I don't have any magical ability. When I was a kid, I had a romanticized notion of mathematics that hard problems were solved in eureka moments of inspiration. But with me, it's always like, let's try this. That gets me part of the way there. Or that doesn't work. Now let's try this. Or there's a little shortcut here. You work on it long enough, and you have to make some progress towards a hard problem by a backdoor at some point. And at the end, it's usually like, oh, I solved the problem. And at least for me, that resonates. I mean, that's also how I feel like at the end of the problem. It's not just like you got to sit there and wait for like the ultimate inspiration to strike you. You work on it, and you make a little bit of progress every time you think about it. So, I mean, it's very hard to give tips on how to find proofs, but I tried to think of some tips that, I don't know, maybe can help you when you're working on the homework. So here we go. Tip 1, please read and understand the problem carefully. I mean, it's really important that you actually understand exactly what you're trying to prove. Try small cases. So, I mean, many problems are of the form, show that for all n something happens. So really, try n equals 1. Try n equals 2. Try equals n equals 3. OK? Practice on the small cases. This is how you build up intuition for the general problem. Number 3, try to develop some good notation. I mean, it's very helpful if you can sort of come up with a more careful or rigorous way of looking at the problem. This is another one. It's a little hard to explain right now, but I like to tell people, put yourself in the mind of the adversary. The adversary is like your enemy who's trying to like prove the statement that you're trying to prove wrong. So try to think about like how you would show that the thing you're trying to prove is false, or like if you're trying to show that like no such blah 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 exists. Imagine an adversary who actually is claiming to you that such a thing does exist, and how you would like fight against that adversary or question the adversary to pin them in a lie. Try to, as you go along, once you solve like some part of the problem, make sure you kind of clarify it, summarize it, write it down as a lemma, put it in the bank so that you can remember and understand parts of the puzzle that will help you later. This is a bit more sociological. Try to use like blocks of like, I don't know, like an hour. Like, don't just be like, oh, I got 11 minutes. I'm going to try to think about that homework problem. Like, it just takes you 11 minutes to remember what the problem is. So, I mean, take it seriously if you're going to sit down and try to solve a problem. On the other hand, take some breaks. I mean, if you've been working on it for hours and hours and you're not making any progress, it's good to give your mind a rest. Also, try to use plenty of paper. This one sounds dumb, but like for me, this is big. Like sometimes I have like half a scrap of paper left. I'm like, OK, I'm going to just solve it on here. Just get up and get some paper so that you can actually try to express yourself. Collaborate. That's very important. You're going to be working in groups, and having other people bouncing off ideas off you is important. And actually, I couldn't think of a 10th one, so we'll leave it at 9. Yeah, the cilantro. Yeah, that's good. That's a good one for next year. So I tried to, I didn't want to just not walk the walk. So this is something I did a couple years ago. I saved this slides from a while ago. See, a few years ago I was teaching this course, and I was talking with the TAs, and we're like, what problem are we going to put on the next homework? Oh, really? You guys know this one? Oh, this is super awesome, actually. This is going to make this like infinitely more exciting. So, okay, so here's the deal. So I was talking to the TAs. I was like, should we put, it was like 2011 or something. I was like, you know, we need some problems to put on the next homework. And the TAs, we were looking through past homeworks for good ones. And I was like, oh, I never saw this one before. So I was like, what about this one? Could it be good? And the TAs were like, no. That problem's like way too hard. Like it killed the students last year. Like don't put it on the homework. And I was like, okay, fine. So we didn't put it on the homework. But then later I was like, okay, what is this problem that like is so hard that like, you know, they didn't put on the homework? So yeah, maybe you guys all know the problem. It's like you have a grid, and there's like a number in each grid, and everybody, the top P people, whatever, it doesn't matter. There's some parameters, P and Q. You got to solve some problem. So I was like, I'm going to try it, and I'm going to try to record my like thought process doing it. So this was me like several years ago. I like sat down at my desk. I'm like, I'm going to try to solve this problem. So this is also not important, but this is like my first page of notes, and I was like, okay, that's good actually, because I don't know what it actually says, but you know, try small cases is one piece of advice. And indeed, if you squint, you can see that here, like I was like, okay, let's try P equals 1, Q equals 1. And that is a very easy case, so I did it. So then I was like, let's try P equals 2 and Q equals 1. And that's also pretty easy, so I did it. And then I did 3 and 1. And actually, I kind of got into some good notation here, which helped me out. And this is where one thing I consolidated. It turns out, at least for me, that like if one of the numbers Q is 1, then it's kind of easy to solve. So I was like, this is good. I'm going to put it in the bank, write down my complete understanding of why it's done if the numbers are 1 in anything. That was like 12 minutes. Okay, so this is my next piece of scratch paper. And it's like, okay, so what's next? The smallest case is 2 and 2. That was kind of harder. And so this is where like kind of being the adversary, I think, comes in. So you have to prove that like at least so many people get prizes when P is 2 and Q equals 2. And here I was really trying to spend time trying to find a counterexample. Like how can I show that that's false? Like what would it look like if not those many people got prizes or whatever the problem was? And you know, by doing this, by trying to figure out what breaks the problem, you kind of come to understand a little bit why it should be true. And maybe you kind of feel for why it's true, even if you don't know how to prove it. I developed some better notation here. Here I was like, okay, now I have a strategy. I'm going to try to prove this by induction, which is usually a good strategy for these sorts of things. I was like half an hour into it. There's a problem, though, with this problem. At least I found that, you're trying to prove something by induction, and then you reduce it to like the smaller case, but then somehow it didn't really exactly match up with the induction hypothesis. So I kind of got stuck. So maybe you need to take a different induction hypothesis. Now I was kind of getting a little tired, and it was like 1 hour. So I was like, okay, now I'm going to take a break. At least I was using lots of paper. That was number 8. So for me, taking a break equals watching TV, which pretty much means watching Survivor. That's my favorite show. So I watched some Survivor. Final Tribal Council was over. I got back to the problem. I was like, all right, I'm renewed, I'm refreshed. I'm going to try that induction again. Figured out some strengths of the induction hypothesis seemed to work. I read the problem carefully. I think that was tip number 1, to make sure that the base case was still okay. It was like another batch of time. And then here, I more or less at this point kind of solved it. And again, it wasn't like, a aha moment where I was finally like, yes, I got the clue. It's just like, all right, I finally put all the pieces together, and I think I more or less solved it. So I kind of sketched out, tried to consolidate what I figured out. I sketched out the basic gist of it. That was like 75 minutes later. And then I felt I kind of more or less solved the problem. So, okay, you can try it yourself if you didn't in concepts, have a little race with me. Then, of course, if this were 251 homework, then I would practice write my proof. Like I would write it all down 100% from scratch so that I could really go into Wednesday night, like next week, knowing I know how to write down the proof. Now, it took some effort. And one thing I want to comment on is, okay, if you actually look at, let's say, what my final proof was that ideally I would turn in for homework, proof is actually kind of short. I used 10 pieces of paper, but the final proof is like half a page long. And if you look at it, it does seem to have some like magical moments, like where how did the person who wrote this proof know to do this or that at that stage in the proof? That's because most of the cognitive process that went into like finding the proof, like all these 1% adding up, was missing from the final product. And in some ways, that is how we do math. This is the idea that this guy, the most famous mathematician, Gauss, championed, that you should totally eliminate all traces of how you figured out your proof. That's a little rude. I kind of think he was sort of a jerk for this, because he even hid all of the explanations of how he came up with his proofs. But it is kind of like that when you're reading the solutions that we give out to the homework. You're like, oh, how could I have come up with this? And you got to realize that it's not just somebody comes up with this by like a magical insight in their brain. It's like the result of a long process of trying things, figuring things out, revising things, cutting things down, and so forth. Actually, on that subject, there's an interesting topic that people have been talking about somewhat recently called open notebook mathematics, where people kind of actually do their mathematics research projects in like sort of an open source way, where they actually record all the thoughts that they're thinking on these projects. And one interesting such project was started by this person, Tim Gowers, who's also a Fields medalist, called the Polymath Project. And it's kind of cool. If you go here, you can see like examples of like actual mathematicians like writing notes to each other, trying to like solve a new problem in mathematics, and see like their thought process and false starts and so forth and so on. Okay. Well, that's the last thing I want to say about how to find a proof. And last thing I'll talk about tonight is how can I write a proof naturally so as to get full points on the homework. That's what you're probably mainly interested in. Well, let me stress that your homework is not like the four-color theorem in more than one way. It's not as hard for one, but also there should be no debate when you've written your solutions whether or not it's a proof, okay? That sometimes happens for these super complicated theorems, but it's not going to happen in 251. So once you write your proofs, your TAs will be able to correctly decide whether you've written a valid proof or not. Okay? So how are you going to do it? So here is the mindset that you should have when you're trying to write your final proof of a homework problem. One thing you can think about is like imagine your TA was going to be like Thomas Hales, or your TA was going to be like Russell and Whitehead. Your TA was going to take that thing that you turned in English and try to turn it into a formalized, 100%, fully rigorously checked computer code. It'd be like you're providing a spec of the proof that they can turn into like a completely rigorous proof, okay? So this is how you should think about it. I mean, you're not doing like the, the formal proof yourself, but you're trying to write, in English in a way that leaves no doubt about any aspect of the proof, leaves no doubt about how to complete any of the steps, and is going to completely cover all the cases, and is going to be 100%, rigorous from start to finish. Okay. Another way, okay, so this is a picture, I guess. Right, so you want to give like a spec to them so that they could implement it perfectly. In other words, you have to convince your TA. This is really, since the TA is the person that's going to be reading your proofs, this is the person that you really sort of want to be in a dialogue with, that you have a complete, correct proof. And this also kind of answers a little bit the questions of like what level of detail should I go into when I'm giving a proof. It depends if you're proving something to a 6-year-old or proving something to a research mathematician, how much proof you give for each deduction. And in this case, your audience is the TAs. Another perspective is like that of a lawyer. You got to present an airtight case, and your TA is going to be like the picky judge that's going to go through every aspect of what you wrote and try to find any logical gaps that might be in there. So here's some possible complaints or responses or points off you might get from your TAs when you write a proof. Some of these you might be used to, like the TA might say, well, the statement A that you wrote doesn't logically follow from statement B. Or you missed a case. Or what you wrote is true, but you didn't sufficiently justify it. Okay, these are common reasons where you might lose points. I also want to emphasize some other reasons you might lose points, though. For example, I don't understand your proof. This is like a valid response that your TAs are in some cases going to have. Okay? So you have to really make sure that they understand what you're doing. Or this explanation is unclear. That's a legitimate complaint for them. Or your proof is very hard to read. Okay? So indeed, as I mentioned last class, 20% of the grade is reserved purely for presentation. And these kind of complaints enter into that. Okay. For the last whatever minutes, I guess it doesn't really exactly matter when we end, I want to kind of do it in, look at some proofs from the mindset of the TA. So this is a comic strip I like to read. It appears in some British newspaper. It's called You Are the Ref. When I was a kid, and maybe still now, I really liked this legalistic mind of knowing the rules. And so this is a comic strip about soccer, where they present some super obscure situations. And you have to decide, if you were the ref, how would you judge? Do they get a yellow card, or do you do a drop ball, or whatever? So the remainder of the slides are kind of like this, but you are the TA. So we're going to look at some proofs, and you'll tell me what you think is right or wrong about the proofs. Okay, here is a problem. It's a pretty simple one, but it could appear on homework. Prove that n squared is greater than or equal to n for all integers n. So here is a proof that somebody wrote. I'll let you read it. And there's a problem with this proof. So let's see if you can find the problem with this proof. Okay, what do you think? Yeah? Yes, this problem actually is a little bit weird. That's the correct answer. You see, if you look carefully up here, it's asking you to prove this for all n, integers n. But this proof actually only proves it for all non-negative integers n. Okay, so it's a picky case. But, this is not a valid proof. And this is the example of a case where you have to prove everything and read the question carefully. Okay, so that's kind of the moral of that one. Okay, some of the proofs are about induction. Suppose you're trying to prove something by induction. What is the problem with this statement? Any suggestions? No, it's valid. Yes? Yeah. That's right. This is actually what you're trying to prove. You just assumed it, that f of k holds for all k. You've got to be careful about what you're doing here. Here's another thing where somebody's trying to prove something by strong induction. Let's see how you feel about this one. Or can you spot a flaw in this one? We'll take a second. Assume these ... dots are okay. Okay, so what is the problem? Yeah? That's right, yeah. This k is not a real variable, right? It should be n plus 1 here, not k plus 1. Okay, so sometimes you get in a routine with these proof strategies, but you got to, do it the right way. All right, so you're pretty good. You found some good flaws. Let's see if you can get this one. This is an actual problem from many years ago. How many ways are there to arrange C club symbols and D diamond symbols in a row such that all the clubs are consecutive? That's the problem. Here's the solution that somebody might write. Any number of between 0 and D of the diamonds, and then the string has to have all the clubs in the row, and then you just have the rest of the diamonds. So everything is determined by the number of initial diamonds, which is one of D plus 1 possibilities. So the answer is D plus 1. So this has a problem. Well, you answered the last one, so I'll wait a bit. Okay, do you want to say? You have your hand up, yeah? Yes, there's this is kind of there's one annoying case you did not account for. This proof is actually fallacious if C is 0, which is possible. If C is 0, then there's only one possibility that's all diamonds. So, okay, this is just, again, trying to get you in the mindset that you have to think carefully about the problem and really check all the cases, not just sort of the obvious cases. All right. All right, let's see if we can find the problem in the following proof. This is actually one that is going to come up for us when we study big O. It's important to know that 2 to the n is bigger than n for all integers n, at least 1. So what is the problem with this proof? Let's take a look. Okay, anybody find a problem with this proof? Maybe we should ask an actual TA. We have a few here. Anyone spot a problem? Okay, I'll tell you. Yeah? Yeah. Here it's okay because, I mean, we need to prove greater than, but we have a greater than here. So is this okay? Okay, the problem with this proof is it's not written in English. Okay, this is also very important. So I mean, if I were the TA, let's say I'm the TA and I'm grading this proof, this is what I would write. It'd be like, is this a definition? Is it a claim? Like, you cannot just start like this. What does this check mark mean? Is this a claim? Is this an assumption? Now I'd be like upset, and I'd be get sarcastic, like, oh, apparently you're doing an induction now. Okay, why? This is not a full sentence. Okay, many points off. All right? I mean, your proofs have to be properly written in English with full sentences. Okay, this is another genuine, these are actually both genuine problems from old 251 homeworks and genuine, I don't know if I should do this, but these are genuine solutions that people had turned in. This is an interesting problem. Again, it's not really important what the problem is, but I'll say it anyway. You have a circle of 15,251 chips. They're all green on one side and red on one side. Did you do this in concepts last year? No? All right. Okay, initially, they're all green side up. In one step, you may take any 4 consecutive chips and flip them. And then you can do this much of times. Is it possible to get all of the chips showing red? Okay. I'll just tell you the answer is no, and this is the intended solution. The intended solution is as follows. Whenever you flip 4 chips, after a while, maybe some of them are red, some of them are green, but let's say g of them are green, then after flipping them, 4 minus g of them are green. That's just how the flipping works. And notice that g and 4 minus g have the same parity. In other words, they're both even or they're both odd. So whenever you do a flip, the evenness or oddness of the number of green chips doesn't change. And it starts out odd number of chips being green, so like you can never get down to 0 chips being green because it'll always stay odd. Okay, that was the problem. Okay, so this is one thing that somebody turned in. They said, no, it's not possible. Let's assume for contradiction, we converted all 15,251 chips to red. But this means in the very last step, there must be 4 consecutive green chips, and the remaining 15,247 must be red. That's actually true. Repeating this k times for k like this many, so they're imagining that like, how would you get there? You flip 4 chips at the very end to red, and then you flip the previous 4 chips to red, and so forth. We get 3 consecutive red chips, but we started from all green, and that's a contradiction. Okay, I won't ask you what's wrong, but I mean the point of this is, if you're asked to show that something is impossible, and this is typically a somewhat tricky thing to show, it doesn't suffice just to show that one particular method of trying to solve the problem doesn't work. Okay, you really have to argue that there's no possible way to do this. You can't argue that like the most obvious way of trying to do it doesn't work. Okay, then there's a part B to this problem, which is the same question, but where you're flipping 7 consecutive chips. Okay, now you actually see the old argument doesn't work, because if you flip 7 chips. Let's say g of them were green. Then 7 minus g of them will be green after the flip. But if like g is odd, then 7 minus g is even, and vice versa. So actually, every time you flip 7, it does change the evenness or oddness. So that old argument doesn't work, and maybe it is possible. Now in this case, it actually is possible. And now here it does suffice just to show one way of doing it. That's all you have to do if you want to show that it is possible. Just explain one way, like an algorithm, if you will, for doing it. So this was the intended solution. Yes, let's number the chips from 0 up to 15,250. And then it just tells you what to do. Flip 0 through 6, then flip 1 through 7, then flip 2 through 8, then flip 15,250. It's a circle, so like through 5. And then observe that every chip got flipped exactly 7 times, which is an odd number, so every chip will in fact end up red. Okay, so that's a good, nice proof. One thing to say is, it didn't ask you to find like the best way to do it, so you don't have to be, there's no extra points for doing it in a clever way, and this is like a nice way to do it. So let's see what some other people wrote. I think this is our last solution. So this is one solution that was turned in. OK, at any given time, let g be the number of chips showing green and r the number of chips showing red. The possible remainders when a number is divided by 7 are 0, 1, 2, 3, 4, 5, 6, and 7. Well, it's close. A flip that involves 6 red and 1 green increments the current modular class of g by 5, while the move that involves 1 red and 6 green decrements the current modular class of g by 5. Originally, with the number of 15,251, the modular class of g mod 7 is 5. Thus, it is possible to make all chips red. So what? Okay, this is an example where like it's legitimate for the TA to just say this doesn't make sense. I mean, you have to structure your proof in a logical way and really explain it. So, in short, this actually goes especially for like the tests too. Do not just write like a bunch of facts that are true and like hope that somehow together they make a proof. Okay? I mean, you have to write a coherent story. OK, so my final proof writing tips. This is also, I think, all I'm going to say. One thing I suggested or mentioned is a proof is like an essay. OK? It's not just a calculation. You have to write properly in English. You should really state your proof strategies and outline what you're going to do. If it's a complicated proof, you should even just write the idea of the proof first. You should keep a linear flow so that you don't first prove this, then prove that, then prove that, and put it all together. But at the same time, if it's a long proof, you need to structure things. We talked about this in the very first couple of slides. Be careful when you use the word obviously or it's clear that. You should really only do that when a proof would spring to mind for anybody who is reading it. And to finish, try to tie everything together and explain at the end in a nice conclusion why everything follows. OK, I guess speaking of conclusions, that's it for this. Thanks for coming. I guess I'll see you in like 13 hours, which is a little distressing, but